a couple more examples of explicit calculations in a non-prime mod. So here's one where we're going to start out the same way, but it's going to look a little different. So let's do 7 to the 29th mod 69. The first thing, as usual, I would do is just go ahead and calculate the phi. Phi of, well, it's 3 times 23. There's not prime powers, there's just two primes multiplied together. So it's just the 3 minus 1 times the 23 minus 1, and you get 44. Okay, so that's good to know. 7 is at a reduced residue? Absolutely. It's relatively prime to 3 times 23. But it's not terribly helpful, unfortunately, because this 29 exponent is not very near 44. And so when we consider another exponent in a minute, it'll be helpful, but it's not directly helpful. So what we really have to do is roll up our sleeves and actually calculate 7 to the 29 pretty directly. But it's really, really important. We're not going to just pop it into a calculator, because that gets really dangerous when the mods get a bit bigger. And we're also not going to just do it absolutely by hand, 7 to the 2, 7 to the 3, 7 to the 4, 7 to the 5, 7 to the 6. That would be a huge pain. And we're going to use the repeated squaring technique. Okay, so here we go. Okay, one more. Okay, so what I'm first going to do is I'm just going to calculate 7 to the 1, that's easy. 7 to the 2, that's just 7 squared is 49. And then I'm going to keep squaring, and so I can get a table that's only of 7 to the powers of 2. 7 to the 2, 7 to the 4, 7 to the 8, 7 to the 16. And then we're going to use those as building blocks and just have to do a few more multiplication tables, a few more multiplications to get the actual 7 to the 29 we want. Okay, so 49 squared is the first hard one. That you can totally use a calculator for. It's 2401. Reduce it mod 69. Now this is the kind of thing that if your calculator or computer system has a mod function, it'll get the right answer because there's no rounding involved. It's a very nice small integer. And that's going to be, turns out to be 55. Okay, so these are about the level of calculation that we really have to do if we're going to do this, what I would say by hand, but using a calculator where appropriate for just the basic arithmetic. All right, so now square 55. That's going to be 3025. Mod 69, not too hard a calculation on a calculator, turns out to be 58. Okay, so now we're up to what is 7 to the 8th, because I've squared 7 1, 2, 3 times. One more, square 58, 3364, it turns out, mod 69 is 52. Okay, and so that'd be great if we were actually just asked for 7 to the 16th, for example, or 7 to the 8th. We'd be done. But that's not true. We're not actually asked for 7 to such a special power that you can get directly by repeated squaring. But now we're going to use that. You can just use these as building blocks. So I repeated the 7 to the 16th over here is 52. Okay, now I'm going to get closer and closer to 29. Let's see, can I add in an 8 to that? Absolutely. Okay, 24 is 16 plus 8. And so what I'm getting here, let me go ahead and make sure that this is clear. I'm using the fact that 7 to the 24th is 7 to the 16 times 7 to the 8th. Because, of course, exponents add, I'm using the fact that 24 is 16 plus 8. So it's all about rules of exponents as usual. Okay, so I'm taking the 52, one of my building blocks, times 58. Yes, I do have to do that. It's a 4-digit number. I have to reduce it mod 69. I use the calculator. And that's 49. Okay, now what can we add in? Can we add in what other power of 2 can we add in? Ooh, a 4. That's not going to overload us. That's going to get to 28. That's still less than 29. So one strategy is just go up to the biggest power of 2 that will fit, do all the powers of 2 from 1 through that, and then do the 16 in this case, and then just add in all the ones that'll fit. And they'll either fit or they won't. You never have to do 2, for example, because there's no point in multiplying in 49 twice because I've already got the result of that, which is 49 squared. Okay, so now what have I got? Let me just expand this out. This is 28. What I'm realizing is that is 7 to the 16 times 78 times 7 to the 4 because I'm expressing 28 as 16 plus 8 plus 4. Okay, so now I've multiplied in that 49 times the 55 for my building blocks over here. Turns out to be, again, a 4-digit number, mod 69. Turns out to be fairly simple, 4. Okay, so that is 7 to the 28th. That's all of this stuff. So far that's just 4, and now to get to all the way to the 7/29th, I just have to multiply in 1 more power of 7. So this is all based on the fact that it's 29. If you express it as a sum of powers of 2, it's 16 plus 8 plus 4 plus 1. Something that if you work with computers a lot, if you do binary arithmetic, this is basically expressing 29 in binary. If you're not used to it, then this is a nice little introduction to that idea. Okay, so I multiply in, that 4 was all of this stuff, and then multiply by 7. Hey, that's something I don't even need the calculator for, and you get 28. So this is pretty cool. It's really neat that with very low technology, basically just almost just 4-function calculator stuff, we're getting a pretty sophisticated answer that 7 to the 29 is going to be equal to 28 mod 69. Now, one thing I could use that for is suppose somebody asked me then for 7 to the 117. Okay, well now 117 is bigger than my phi function. 117 is 88 plus 29, as it happens. Okay, and so that says that 7 to the 117 is 7 to the 88 times 7 to the 29. Okay, or in other words, 7 to the 44, hello, squared. And now I can use Euler. Okay, and so that's just going to be the same thing. That's just 1 squared times 7 to the 29, and that's going to be that previous result. So as soon as you get past 44 in this case, and in general, as soon as you get past the value of the phi function, remember that was up here, then you can just take out, you can just do the exponent mod that phi value. And the biggest, in this case, for example, the biggest power you're ever going to need to explicitly calculate of 7 is like 7 to the 43rd. Okay, so there's this twin-pronged strategy of using Euler wherever you can, and then using repeated squaring if you absolutely need to. And that's really what something like Wolfram Alpha most likely does, is it exploits exactly these theorems and these techniques to do these calculations quickly with really, really big numbers. Remember, though, that so for the first calculation, for this 7 to the 29, it didn't matter at all that 7 was a reduced residue. This kind of strategy works no matter whether it's reduced. But when we looked at the second part, this fact that 7 to the 44 was automatically equal to 1 with no calculation required, that really used, let me put that down, this used that 7 was a reduced residue. Okay.